On February 14, 1990, a machine the size of a small car drifted through the darkness roughly 6 billion kilometers from the planet that built it. Voyager 1 had launched from Cape Canaveral on September 5, 1977, chasing a rare planetary alignment that would not repeat for another 176 years. By this Valentine's Day, it had already flown past Jupiter in 1979 and Saturn in 1980, sending home the first close portraits of their storms and rings. Now it was far beyond Neptune's orbit, climbing above the plane of the planets at more than 60,000 kilometers per hour, deeper into space than any human object had ever traveled. From this vantage point, the sun was no longer a warm disk. It was a bright star among countless others, its light nearly 6,000 times fainter than it appears from Earth. The planets that had once loomed as destinations were reduced to scattered pinpricks, lost against the black. Voyager 1 had completed its scientific mission years earlier. Its instruments still measured magnetic fields and charged particles, but the cameras had gone dark, no longer pointed at anything worth photographing. The spacecraft carried 3 radioisotope thermoelectric generators, fueled by decaying plutonium-238, and every year that power supply weakened. Engineers knew that eventually there would not be enough electricity to run everything. Against this backdrop, something improbable was about to happen. Mission controllers at the Jet Propulsion Laboratory in Pasadena, California, prepared to send a command that would rotate the entire spacecraft, turning its scan platform back toward the inner solar system. The plan was to make Voyager 1 look over its shoulder at the worlds it had left behind, and to photograph them as a single family, all at once, from a distance no camera had ever attempted. It was a request that had nothing to do with science and everything to do with perspective. No prior mission had ever tried to capture the entire solar system in one frame from the outside looking in. To understand why this photograph was taken at all, we have to understand the man who spent years fighting to make it happen, and the resistance he faced. The idea belonged to Carl Sagan. As a member of the Voyager imaging team, Sagan had argued since the late 1970s that before the cameras fell silent forever, the spacecraft should turn around and photograph Earth from the outer solar system. Not for the science, he admitted, but for the meaning. A picture of our world as a mote of dust, seen from beyond the planets, might change how humanity thought about itself. But the request met years of resistance. Engineers at the Jet Propulsion Laboratory had practical objections. Pointing the cameras back toward the inner solar system meant aiming them dangerously close to the sun. Even at 6 billion kilometers, direct sunlight could burn out the sensitive Vidicon tubes inside the cameras, destroying them permanently. The imaging system was still needed, in principle, for possible future observations. There was also the matter of resources. Executing the maneuver required spacecraft time, ground station time on the Deep Space Network, and the labor of a team already stretched across multiple missions. To many managers, spending those resources on a picture with no scientific return was hard to justify. So the proposal waited. It waited through the Jupiter encounter, through Saturn, and through the long years afterward. What finally cleared the sequence was timing and authority. By 1990, Voyager 1 had completed all of its planetary science. The cameras were no longer serving any active investigation, and their power draw was becoming a liability on the aging spacecraft. The risk to the instruments no longer mattered as much, because the instruments were about to be retired anyway. Sagan's persistence, combined with support from senior NASA figures including Administrator Richard Truly, tipped the balance. The order came down. Before the cameras were shut off for good, Voyager 1 would take one last set of images looking homeward. Engineers scheduled the sequence for mid-February 1990. But approving the photograph was only the beginning. The team now faced an extraordinary technical problem. They had to command a spacecraft they could no longer see, aim its cameras near a blinding sun, and hit targets that were little more than specks of light in an ocean of darkness. The central danger was the sun. Even from 6 billion kilometers away, our star remained the brightest object in Voyager 1's sky, and pointing the narrow-angle camera too close to it risked destroying the light-sensitive detectors instantly. The imaging team had to calculate exact angles, ensuring the camera swept across the planets while never staring directly into the solar glare. Earth itself sat only a few degrees from the Sun as seen from Voyager's position, making it one of the riskiest targets in the entire mosaic. Precision was everything. To photograph objects that appeared smaller than single pixels, the spacecraft's orientation had to be controlled to a fraction of a degree. Voyager 1 used a combination of a star tracker locked onto a reference star and small hydrazine thrusters to rotate and hold its position. Engineers modeled where each planet would appear in the camera's field, accounting for the spacecraft's motion and the geometry of the outer solar system. Then came the problem of distance. Voyager 1 was so far away that a radio command traveling at the speed of light took more than 5.5 hours to reach it, and another 5.5 hours for confirmation to return. There could be no real-time steering. Every instruction had to be uploaded in advance, encoded as a sequence the onboard computers would execute on their own, hours after the humans had sent them. The commands were transmitted through the Deep Space Network, using massive antennas to reach across the void. Once the sequence began, the team could only wait. Voyager 1 rotated its scan platform, locked onto its targets, and opened its camera shutters on schedule, executing a choreography written entirely from Earth. The spacecraft captured its images blindly, storing them onto an onboard tape recorder, since it could not transmit them fast enough in real time. Nobody on the ground knew yet whether the aim had been true, whether the Sun had been safely avoided, or whether the planets had fallen within the frames at all. What Voyager 1 was recording, one careful exposure at a time, would become the first and only portrait of our solar system taken from the outside. The full sequence consisted of roughly 60 images, a mosaic designed to sweep across the solar system and capture as many planets as possible in a single session. To cover such a wide arc of sky while still resolving distant worlds, the team used both of Voyager 1's cameras in tandem. The wide-angle camera captured the broad context, the sweep of space and the position of the Sun, while the narrow-angle camera zoomed in to record each individual planet as a distinct point of light. The result was not a single photograph, but a family portrait stitched from many frames. 6 planets appeared in the mosaic: Venus, Earth, Jupiter, Saturn, Uranus, and Neptune. Each was little more than a speck, a few pixels at most, scattered across a background of empty darkness. Jupiter and Saturn, the giants, were among the easier targets because of their size and brightness. Uranus and Neptune, far dimmer and more distant, required longer exposures to register at all. Some planets were absent by necessity. Mercury was lost in the Sun's glare, too close to the star to photograph safely. Mars did not register clearly, its light insufficient to appear in the frame given the geometry and exposure limits. Pluto, small and faint, was simply too dark to capture. The portrait was never meant to be complete. It was meant to be honest about what could be seen from such a distance. The imaging team carefully documented where each planet fell within the mosaic, matching pixels to predicted positions to confirm the aim had worked. When the frames were later assembled, they showed the planets strung across the sky at different angles, each isolated in its own patch of black. A scattered arrangement that reflected the true, sprawling architecture of the solar system, rather than the tidy diagrams of textbooks. Together, these 60 frames formed something no one had ever seen, the worlds of our Sun photographed from beyond them, reduced to their true scale in the cosmos. Yet within this collection was one frame that would eclipse all the others in meaning. It captured a single, unremarkable point of light, one that happened to be the only home our species has ever known. In one narrow-angle frame, Earth appeared as a single pixel, a pale blue point suspended in a shaft of scattered sunlight. That beam of light was not part of Earth at all. It was an artifact, sunlight glancing off the camera's optics, and by chance, our planet fell directly within it. The effect was accidental, but the result was unforgettable. Our entire world, reduced to a bluish speck, caught an array of glare. The numbers underline how small Earth truly was in the data. From 6 billion kilometers away, the planet occupied less than a single pixel of the image, measuring roughly 0.12 pixels across. Everything human beings had ever done, every ocean, every mountain, every person who had ever lived, was contained within that one dim point of light, smaller than the grain of the image that recorded it. Carl Sagan gave the image its meaning in words that would outlast the mission itself. He described Earth as a pale blue dot, a lonely speck in the great enveloping cosmic dark. On that dot, he reflected, played out the entire history of our species, every conflict and triumph, every empire and belief, all crowded onto a mote of dust suspended in a sunbeam. Seen from beyond the planets, the boundaries and divisions that dominated human life vanished. There was only the fragile point, alone in the vastness. The scientific value of the frame was essentially zero. It taught nothing new about Earth's atmosphere or geology. Its power was entirely one of perspective. A mirror held up from the edge of the solar system, showing humanity its true size against the indifferent scale of space. It was the first time our world had been photographed as a point among the stars rather than a globe holding a lens. But this image, and the 59 others taken alongside it, still existed only as data recorded on a tape recorder aboard Voyager 1, billions of kilometers away. Before anyone on Earth could see the pale blue dot, those frames had to survive an extraordinary journey home, transmitted as the faintest of whispers across the emptiness of space. Capturing the portrait was only half the task. At 6 billion kilometers, Voyager 1 could not send images the instant they were taken. Sunlight itself, traveling at 300,000 kilometers per second, needed more than 5 hours to bridge that gulf. A radio signal from the spacecraft faced the same crawling journey, and it arrived impossibly faint. By the time Voyager's 23-watt transmitter reached Earth, its signal had weakened to a fraction of a billionth of a watt. To catch that whisper, engineers relied on the Deep Space Network, the ring of giant antennas at Goldstone in California, Madrid in Spain, and Canberra in Australia. The largest of these dishes stretched 70 meters across, curved metal bowls straining to gather a signal quieter than starlight. Before any of it could be transmitted, the 60 frames were recorded onto Voyager's onboard digital tape recorder, a device using magnetic tape wound on reels, storing each image as raw numbers rather than pictures. Every frame held 800 by 800 pixels, each pixel carrying a brightness value. The spacecraft played back that tape slowly, streaming the data home at rates that seem absurd today. Depending on conditions, Voyager could return information at only a few hundred to a few thousand bits per second, a trickle compared to any modern connection. The images did not arrive in a single afternoon. They came in fragments across weeks and months, piece by piece, as the great dishes tracked the spacecraft across the sky and pieced the numbers back into pictures. The final images of the family portrait were not fully received until May 1990, 3 months after the shutter sequence. When the pale blue dot frame was finally assembled, it revealed Earth occupying less than a single pixel, a speck of light 13% the size of one picture element, floating in a band of scattered sunlight. Everything humanity had ever done rested inside that fraction of a dot. But even as those precious numbers were still crawling homeward, mission controllers were already preparing an irreversible decision. The cameras had done their work, and the spacecraft was running low on the very power that kept them alive. Voyager 1 carried no solar panels. So far from the sun, sunlight was useless as a power source. Instead, the spacecraft drew energy from 3 radioisotope thermoelectric generators, devices that converted the heat of decaying plutonium-238 into electricity. At launch in 1977, those generators produced around 470 watts. But plutonium-238 decays with a half-life of roughly 88 years, and the thermocouples that turned its heat into current degraded steadily. Every year, Voyager lost about 4 watts of available power. By 1990, the spacecraft's energy budget had shrunk dramatically, and every instrument aboard competed for a dwindling supply. The cameras were expensive to operate. Their imaging system, along with the computers and heaters that supported it, consumed power the mission could no longer justify. Beyond the primary planetary encounters, there was almost nothing left for Voyager 1 to photograph. It was fleeing into empty space, where no worlds waited within range of its lenses. The scientific instruments that measured magnetic fields, charged particles, and plasma would matter far more in the interstellar mission ahead. So, mission controllers made a deliberate choice. Shortly after the family portrait was secured, they sent the command to shut the cameras down permanently. The instruction crossed those 6 billion kilometers, and Voyager obeyed. The wide-angle and narrow-angle cameras went dark. The imaging computer, no longer needed, was freed for other purposes. It was a decision made not out of failure but out of arithmetic. Power was a finite resource, and the mission ahead would last decades. Keeping the cameras warm and ready would have drained energy that Voyager needed simply to keep speaking to Earth. The pale blue dot was, in a very real sense, the last thing Voyager 1 was ever meant to see. From that moment forward, its eyes were closed, its attention turned outward toward the boundary of the sun's influence. Many assumed that if the desire ever arose, the cameras could simply be switched on again, but that assumption was wrong. In the years that followed, the ability to command those cameras did not merely fade. It was systematically dismantled. Reviving Voyager's cameras today is not a matter of flipping a switch. The obstacles are physical, digital, and human, and each alone might be insurmountable. Begin with the hardware. For more than 3 decades, the cameras have sat unheated in the deep cold of interstellar space, where temperatures plunge to hundreds of degrees below zero. The optics, the Vidicon tubes, the delicate mechanisms designed to operate warm, were never meant to survive frozen for so long. The heaters that once kept them functional were switched off to save power. Even if commanded to activate, the optics are almost certainly frozen beyond usable condition, their lubricants solidified, their components thermally stressed past reliable operation. Then there is the software. When the cameras were retired, the flight software that operated the imaging system was eventually removed from Voyager's onboard memory. The spacecraft carries only a tiny amount of memory by modern standards, and every byte is precious. Rather than preserve instructions for instruments that would never be used again, engineers overwrote them with code needed for the ongoing mission. The programs that told the cameras how to expose, capture, and record no longer exist aboard the spacecraft. Restoring them would mean reconstructing decades-old code and uploading it across a signal that now takes more than 20 hours to reach Voyager one way. Finally, there is the ground. The original systems built to command the cameras, the specialized hardware, the software tools, the trained personnel who understood the imaging chain, have largely vanished. The engineers who wrote those routines have retired or passed away. The computers that ran the ground support are museum pieces. The institutional knowledge, the undocumented details that made the system work, faded with the people who carried it. NASA could not simply reassemble that expertise. Much of it was never written down. So Voyager's cameras remain closed, not by choice anymore, but by the accumulated weight of time, physics, and forgotten knowledge. The pale blue dot stands as a final image in the most literal sense. There is no going back to that moment. Yet even blind, Voyager still travels, and it still has something left to teach us. Voyager 1 has never stopped moving. Today it races through interstellar space at roughly 61,000 kilometers per hour, more than 24 billion kilometers from the Sun, farther than any object human hands have ever built. In August 2012, it crossed the heliopause, the boundary where the sun's outward flow of particles gives way to the wind between the stars. It became humanity's first true interstellar envoy, still whispering data back across a distance that now takes its signals more than 22 hours to travel. But its voice is fading. Those plutonium generators continue their slow decay, shedding about 4 watts each year. One by one, instruments have been switched off to conserve the last reserves. Engineers estimate that sometime in the 2030s, Voyager will no longer have enough power to run a single science instrument. Eventually it will fall silent altogether, drifting onward as a dead machine for millions of years, carrying its golden record towards stars it will not reach for tens of thousands of years. And yet, the pale blue dot endures, not aboard the spacecraft, but in us. Carl Sagan looked at that speck of light, smaller than a single pixel, and saw everything. Every war, every empire, every love and cruelty and triumph in human history, all of it contained in a mote of dust suspended in a sunbeam. The image did not show us the cosmos. It showed us ourselves, tiny and fragile, against an indifferent vastness, sharing one small world with no refuge elsewhere in sight. That is why the photograph still matters. It was taken by a machine we sent to explore other worlds, which paused, turned, and looked back at the one that made it. It was a gesture of memory, a final act of seeing before the eyes were closed forever. Voyager 1 will never take another picture. Its cameras are frozen, its software erased, its makers gone. But the last thing it ever saw was home. One final look, then darkness forever.